In this video, we'll talk about end behavior of a function. Now, end behavior really can be summed up by two statements. So basically, the idea is as x approaches infinity, y approaches something. It might be infinity, it might be negative infinity, it might be one particular number, but what value is it tending towards? And then the other is as x approaches negative infinity, what is my y doing? Y approaches something. So really, you can fill in this blank every time you're thinking about end behavior. I'm just worried about, if I'm looking at a graph, what's happening at the end on the right and what's happening at the end on the left, at the very, very end. So let's take a look at like a classic example. And this is where it can be very useful to just have a very rough image of a graph for yourself. So I know x squared looks like a parabola. Looks something like this. So if I'm thinking about it, as x approaches positive infinity, my y values, so I'm just looking at the positive side here, as I go out, well, it's going to go up, which means that y approaches positive infinity. And this arrow is just kind of a shorthand in mathematics for approaches, meaning that y will tend towards infinity. It's never actually going to get there because it's infinity, but it goes there. Okay, and then likewise, if I'm looking at the left half, so as x approaches negative infinity, my y also approaches positive infinity. It also goes up as I go left. And that's end behavior for x squared. So let's look at one that's a little more complicated. This one is a cubic equation and it has a bunch of extra terms. Now, as x gets sufficiently large, when we're talking about millions of millions of millions, these extra pieces really aren't going to affect it much. Eventually, this x cubed term is just going to dominate. It's going to be so large, so massive, that these other terms aren't going to affect it as much. So the overall trend is going to be dictated by our leading term, and that's why they call it the leading term test. So if we're trying to look at, or trying to figure out end behavior, all we have to do is look at the leading term. So if we're looking at a polynomial, the highest power term. So if we think about x cubed, just x cubed, it's going to look like this. Now this one will look a little different in the middle, but we don't care about the middle. All we care about is what's happening at the ends. And eventually, those cubic tendencies are going to take over. So in this case, as x approaches positive infinity, y also approaches positive infinity, because we're looking at this half. Eventually, it's going to go up and right. In the middle, there might be a few more hoops, might be a few more swoops, but that is what it's ultimately going to dictate towards. Okay? And then if we look at the left half, as x approaches negative infinity, y approaches also negative infinity. And that would be end behavior for this slightly more complex function. Now real quick, let's take a look at one more example. We're looking at y equals 1 over x. Now, a couple of ways we can look at this. We could look at a graph, we could plot some points and go that way. Or I could look at it and think, okay, what happens as x gets really big? And what happens, okay, it'll be a half, then a third, then a fourth, then a fifth, then a sixth. It's going to keep getting smaller and smaller and smaller and smaller. And if I keep going out further onto the positives, I'm never going to go negative, because a positive divided by positive is still negative, but I'm going to get closer and closer to 0. Now, I'm never actually going to get there, but it'll get closer and closer to 0. So in this case, as x approaches infinity, y approaches 0. And I wanted to show this example just to show that they're not always going to be infinity. It might be a single value. And also in this case, if we think about the negatives, it's going to result in the same 0 for y. So it'd be negative 1/2, negative 1/3, negative 1/4, which is getting closer and closer to being positive, closer and closer to 0. It's never actually going to get there because I'm, again, dividing a positive by a negative in this case to make it to where it'll always be negative, but it's always going to get smaller in absolute value. So this would be end behavior for this function. Now that makes sense because if we look at the graph, Well, there's the positive half. As I go out, it's going to get closer and closer to 0. And the negative half, well, it's going to get closer and closer to 0 there too. So both make sense.